Our next topic is going to be the periodic table. So when you look at the table for the first time, it seems to be disorganized or organized in a way that doesn't seem to make any sense. It's got basically gaps and holes and whatnot in it. And things, sometimes there's symbols with one letter and sometimes there's two letters on it. And there's usually a bunch of numbers and other symbols around those letters. So the whole point of this is not to confuse students. It's actually to make things a lot easier. And then after we hopefully get through this discussion about the table, that you'll look at the table and realize, oh, this actually can help me. So first, a little history with it. Chemists, once we decided that we understood what atoms were after Dalton, and that we were finding atoms, more and more atoms, they decided that they needed a way to organize these. And to this point, before the table came around, they basically just had all the elements, names, and properties on like small cards, and they were just put into a little box. So it reminds me of the thing that my mother and grandmother had with recipes, just a little box with 3x5 cards in it. And you want to talk about carbon, you go find it and you pull it out and you look at it. So the person who's going to get credit for this is called, his name is Mendeleev. He's a Russian scientist. The lore that he says that gives up is that he had all of his little 3x5 cards out, and he had put a bunch of them up on the board and on like a cork board. And then he was standing there staring at them, trying to figure out a way to organize them that made sense. There were attempts at periodic tables that had been out, but none of them were good enough. And some of the ones that weren't too bad were just too much to handle. They had created like a cylinder that was the size of a basketball, but taller. And that wasn't something you could just carry around with you. So what Mendeleev did is he fell asleep staring at his cork board. And when he woke up, he said, this is what he saw. So let me open this up a little bit here. That on his cork board, that's terrible. He had all these cards all over the place with all these names on them. Symbols and whatnot. They were all over the place. That was terrible. And an interesting chance happened. That as he was looking at his table, he noticed that lithium and sodium and potassium just happened to be one on top of the other. And if you look at the periodic table, that's the order in which they are on the table. So as he was waking up, he said he wasn't fully awake yet. He was still sort of in dreamland. He was looking at those cards, and then he realized something, that lithium and chlorine make a 1-to-1 ratio, and sodium and chlorine make a 1-to-1 ratio. That's table salt. And then potassium and chlorine make a 1-to-1 ratio. And he thought that maybe there was some significance to that. So let me get rid of some of this other stuff here. So he asked himself, does lithium form a 1-to-1 ratio with anything else? And it turns out it did. Okay. Well, what happens when I put sodium with fluorine? It's also a 1-to-1 ratio. And potassium, also a 1-to-1 ratio. So now he's getting excited. Maybe he can make a table based off of how things react. Okay. So is there anything else that makes a 1-to-1 ratio? Well, LiBr also makes a 1-to-1 ratio. Sorry, I meant to put Na, Br, Kbr. So now he's certain he's got something going on here. So he's done two things. He has decided that these are a family. And since chlorine, fluorine, and bromine also behave in the exact same way, a 1-to-1 ratio, and he knows fluorine's the smallest one, he puts these guys in a family of their own. Now he's got two portions of the periodic table already ready to go. And so what he does is he keeps doing checks. He's not actually needing to do chemical reactions because people have already done these reactions. So he checks to see what other kinds of substances make one-to-one ratios. He finds out that rubidium makes a one-to-one ratio, makes a one-to-one ratio, makes a one-to-one ratio. So rubidium obviously needs to be included in the family that sodium, lithium, and potassium are in. So he's looking around, does anything else need to go into the bromine section? So if you grab your periodic table, you can see that fluorine, chlorine, and bromine are there, one on top of each other, and then iodine is next. So iodine belongs in this family, but it would only belong in this family if, if LiI was a thing, and it is. NaI, also a thing. Ki, also a thing. Rbi. So now he's figured out reactions that belong together, and he can group these elements in what he's calling families or groups. This one here is interesting because that's the thing that goes along with NaCl. Those two things, you'll find them in table salt, regular table salt, in iodine, enriched table salt. So you can get it with and without, but if you have the NaI inside the table salt, you don't even notice it when you eat it. And you get a minute amount of iodine in your diet, which is what you need, so you don't get goiters. So this was something that manufacturers or distributors of table salt did sometime in the early 1900s, added a little bit of NaI to your table salt, and you didn't notice, except you never got a goiter, which was this terrible thing that your thyroid gets messed up and then it can grow size of a softball. It can be golf ball, softball size. I've seen one size of like a baseball glove, a small watermelon, that they can be pretty disruptive to your life. Okay, so what about this word periodic? So why is it a periodic table? So what he's saying is, as I go through the elements, periodically they behave the same. So if I look at hydrogen, the very first element up there, above it, it has a 1. Well, what does that 1 mean? We talked about that earlier. That's the number of protons that hydrogen has, its atomic number. So then I go hydrogen and then move over to helium all the way on the other side of the table. That's number 2. Why are they not right next to each other? Because they don't belong next to each other, because helium does not chemically react like the elements that it would be above. And in this case, Be, Mg, Ca, all of those in that second column. So it can't be in the second column because it behaves like any neon, argon, krypton, xenon, and radon chemically. So we get the lithium, and okay, so I have this element number 3, lithium, and it behaves a certain way, a 1-to-1 ratio with these elements that I've got here. And then I go to beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and none of those form a 1-to-1 ratio with fluorine. So then all of a sudden I get down to sodium, and there it is again. So lithium forms a reaction. Let me scroll down here. Lithium forms a particular type of reaction, and then I go through this, and boom, sodium makes that same reaction. And then I go again, and so does potassium. So as I'm going through the elements, number 1, number 2, 3, 4, 5, 6, 7, 8, 9, 10, all of a sudden number 11 is just like number 3. And then I go through this again, and number 19 is just like number 11. And I go through this again, and 37 is like 11. So periodically, as I'm going through the elements on the periodic table based off of their atomic number or their number of protons, I find elements that behave similarly. So when you're looking at a column in the periodic table, you should be thinking, okay, those things are going to be behaving similarly. So I'll pull this one out. Copper, money. Silver, money. Gold, money. They're also jewelry. Why are those 3 things? Why are we not making money out of nickel and palladium and platinum? Well, because these guys behave in a particular way that makes them chemically resistant to rusting. I don't want to give somebody a metal coin and have that thing rust. So let's just take it out of it. Let's just use things that don't rust. So they used copper, silver, and gold. And Same thing with jewelry. You don't want to give somebody like a necklace or a bracelet that's expensive and then have that thing rust on you. You would never give anybody a zinc ring. It would, depending on how sweaty they are, maybe last a day or two at most. So those elements behave the same, so they belong in the same column. They belong in the same family. And that's the case with all of these substances, that these things that are in the same column behave similarly to each other. So let's go back up here. If you're in Germany, the Germans will tell you that Julius Meyer did this work before Mendeleev. He may or may not have actually done it before, but he didn't publish before, and that's all that matters. The most important thing in science, as far as who gets credit, is are you telling everybody or not? And Myers didn't tell everybody before Mendeleev, so he doesn't get credit for it. So the columns are vertical, and those guys are called groups, and the rows, the horizontal sections, those guys are called periods. So things in the same column are going to behave similarly. Things in the same row might behave kind of like each other if they're right next to each other. Like sodium and magnesium have some properties that are kind of similar, but not nearly as similar as the things that are above and below sodium. But as you move across the table, the things become very different. Sodium is very different than chlorine, very different than argon. This is Mendeleev's first handwritten scratching out of his periodic table, and then somebody typed it up and it looked like this. And again, well, here's a picture of Mendeleev. And then we get to this spot where we've got something organized and all the elements that we know and have made all the way up to element number 118. Not all of these things are super useful to us, but do a brief overview of some of the groups. So there's two nomenclature systems as far as numbering the table goes. Go across the top, you'll see numbers like 1 through 18, and then you also see 1A, 2A, 3A. Those don't make a lot of sense to you yet, but they will soon, as to why they would say 1A, 2A, 3A. The 1 through 18 is really obvious. It's just you number the columns from left to right. So let's talk about these guys for a second. So group 1, so the group that's got lithium, sodium, potassium inside of it, those are very, very reactive. Those are alkali metals. We're going to not associate hydrogen with that because hydrogen is a gas. And you know that because it's green, or well, the periodic table that I wanted you guys to get is green, and then the elements that are green are gases, blue are liquids, and black are solids. So those metals, sodium, lithium, potassium, rubidium, cesium, and francium, those guys are all very reactive. As a group, they're called the alkali metals, and when they form a compound, they form a +1 charge, meaning that they give 1 electron away. The second to last column number 7A or column number 17, the one that starts with fluorine, those are also very reactive. And that column is called the halogens. You probably heard that word halogen associated with light bulbs and whatnot. And they're very reactive for the same reason that the first column is very reactive, and that is that they're trying to do one thing. The one thing that they're trying to do for the metals is give away an electron, and one thing that they're trying to do for the halogens is gain 1 electron, which is why in the formal charges you can see this guy's charge is a +1 and that one's a -1, meaning you've gained 1 electron, and this is lost 1 electron. And then this one here would be lost 2 electrons. I don't know why that looks like cost. Lost 2 electrons. And then going along with that, gained 2 electrons. So in chemistry, it's easier to do one thing than it is to do more than one thing, just like in regular life. So if you've only got the one thing to do, you do it very quickly, very reactively, just like get it done kind of situation. And if you have to do more things, you kind of become more lazy about it. So the carbon column, these are lazy. They're like, I gotta get 4 electrons or give 4 electrons. Like that seems like too much work. So I'm just gonna sit here and do nothing. So this is really obvious. If you've got a bag of charcoal, I mean, it could sit there for decades and do absolutely nothing, not gaining or losing 4 electrons. And that's what regular old carbon is just carbon charcoal. Column number 2, these guys are called the alkali earths. They're not quite as reactive because again, they're trying to use 2 electrons. The halogen thing, you know those because of headlights, although we've switched over to the LED, so that's not going to be a thing as much anymore. But the halogen bulbs, they produce a lot more blue light than orange and red light in the spectrum of a rainbow. And blue light provides crispness, and orange and yellow and red lights provide like a blurringness. So if you want a photograph of yourself and you want to look good, like a school picture or some kind of professional photography, they're going to want you to do it at the golden hour, either in the morning or in the evening. So that's when the sun is cutting through a lot of the atmosphere, and the atmosphere cuts away a lot of the blue. And so you end up with a lot more red, oranges, and yellows on the subject. So if you've got a pimple, it kind of gets smoothed out. If you've got any lines like my older face is, they get kind of smoothed out. But if you want to know exactly what's going on with that person's face, you take the shot at noon. That way you'd have the most possible blue light. And that's what the halogens are. They provide more blue light. And so why would I want that on a car? Because I want to know where the road ends. I want to know that that thing on the side of the road is a bush, or wait, no, it's an elk. And if I've got halogen lights, I'm more likely to see that because it's crystal clear. There's a crisp delineation between objects. Same situation with like the operating room. The lights in the operating room have a bluish purple tint to them because you want the doctor to know what the skin is, what the fascia is, what the muscle is, and where the veins are. You don't want any of that to smooth out. Okay, and then the noble gases, that was sort of a joke from scientists. The other name for them are the inert gases. They don't do anything. They're not kind of reactive or mildly reactive, they're non-reactive. You have to do something very violent to the noble gases to get them to react. And it took us a long time to figure out what that thing was, and it turned out to be lightning bolts, shooting lightning bolts through the gas with other very reactive gases. So the reason that it was kind of a joke is because noble gases don't interact with anything, just like nobility don't interact with anything. So if you want to go have tea with Kate Middleton, the Princess of England, she's not going to have tea with you. She doesn't have tea with common people, and the noble gases are like, yeah, no, we're happy. We don't want anything to do with any of you. Okay. So alkali metals, alkali earths, this transition metal section we'll talk about in a bit. These guys are called the lanthanides and the actinides at the bottom. And we'll discuss why those are that. 15 and 16, I found this chart and I like it. I should probably just get rid of those things because nobody ever uses those terms for those. But we use halogens and noble gases for those last 2 columns. The transition metals are metals that transition you from one side of the table to the other side of the table. And we don't talk about them initially because their oxidation states can change, meaning, like I said, the alkali metals will form a +1 in a compound. If I'm talking about copper, it could be +1, it could be +2. It depends on the situation. Same situation with iron. It could be +2, it could be +3, depends on the situation. The lanthanides and the actinides. So here's lanthanum and here's actinum. So that's why they're called those series, because it's the first element in that row. So they pull those apart. And there's a reason that they're at the bottom, and it's really just about convenience. What's that? These elements that are after uranium 92, those are called trans-uranium elements. And we've made all of those. Anything larger than element number 92 are things that we've smashed together in an atom smasher and created. They have very, very little use, and most of them have absolutely no use at all. But we didn't know that until we made them, so that's why we make them. You can see on the periodic table you have that there's color changes between elements based off their solid, liquid, or gas. But then on this one, we've got, are they metals, metal, non-metals, or metalloids? So the metals, you can see most of the table is metals. And those, there's a lot of elements in there whose names you know to be metals, like iron and copper and gold and whatnot, but some other names that you don't know and you maybe didn't realize that those were also metals, like, I don't know, thallium or bismuth or polonium or something like that. And then we've got the non-metals, so all those ones on this thing that are green, and then our metalloids, so the ones that are sort of metals and sort of not metals. And there's a stair step on your table that's black, but they're in this one, it's red. And that stair step is the delineation between the metals and the non-metals. So metals, so let's talk about those for a while. So we've got properties of metals is they're shiny. Okay, so that's luster. They're usually a solid, but not always, because we have mercury that's not a solid. And other elements like gallium that will turn to a liquid at the temperature of coffee. So some of them aren't as rock solid metal at this temperature and pressure, but they're all metals except for the mercury. They have high electrical and thermal conductivity. So electricity can pass through them, heat can pass through them. You can run electricity through a spoon, or you can a metal spoon, or you can make a metal spoon, put it in tea, and then the other end of it gets hot because it conducts that heat well. Malleable and ductile. So these are two things. The malleable one just means you can beat it, you can hit it with something, or you can press it with something really strong, like a hydraulic press, and get it into the shape that you want. Like the quarter panels on your car, they're made out of metal, and it's literally just a hydraulic press that's in that shape, and it takes a piece of sheet metal, just straight metal that looks like a big piece of paper, and it presses it into the shape that it needs to be. So that means it's malleable. Older terms for malleable might be, I'm going to beat this into a shield or pound this thing into a sword kind of situation. And then ductile means we can pull it into a wire. So you can take a large chunk of, say, copper and attach a weight to it, and then heat the copper near its melting point. And then the weight will pull the copper down. Depending on how fast I allow that to happen, I can get a thicker wire or a thinner wire. Yeah, so I can pull them into wire. That's what ductile means. What else I want to say about metals? And you can make homogeneous mixtures with metals, alloys. So like you could take copper and tin and put those guys together and make bronze. Or you can take iron and different combinations of other metals and make different types of steel. So usually what ends up happening is the substance that's an alloy is now more corrosion resistant. It may be more or less flexible than the original substances that are in their elemental form. And most importantly, as far as the chemistry goes, is metals give away electrons. So they become positively charged when they form a compound. By themselves, they're an atom and their charge is zero because their proton and electron number are equal. But when iron forms a compound with, say, oxygen through rust, the iron gives its electrons away. So now let's talk about the nonmetals. They're the opposite. They do not give their electrons away. They accept electrons. Nonmetals want to gain electrons. So iron making a compound with oxygen, the iron is the metal and it gives the electrons to the nonmetal oxygen. They are not lustrous. They are usually gases and well, there's one liquid, bromine. They're not usually solids, like 4 solids, and one of them, maybe 5 solids, and one of them is iodine just evaporates. If you've got solid iodine at room temperature, if you take the lid off the container, it'll just evaporate away from you. They do not conduct electricity well. They do not conduct heat well. So everything we talked about with metals, we don't get to do that with nonmetals. And they also do not form alloys with each other. Well, they will form covalent compounds, which we'll talk about a little bit later. And then the metalloids, these guys are interesting. They have properties, depending on which one we're talking about, of metals and nonmetals. So the best example would be silicon. Silicon can be super shiny, but it's also brittle. So it can't be malleable into the shape of a sword or something like that. It doesn't work like that. It's inflexible, but it can It can be a conductor or it can be an insulator for electricity. So this is why silicon is used in the computer chip industry, and it makes semiconductors. So what a semiconductor is I try to pass electricity through this thing that is supposed to be a conductor, and it doesn't let any electricity through. So that means it's an insulator. And then if I push hard enough, eventually it's just going to become a conductor. So imagine that you're pushing on a door and the door's locked and you can't get it open. And then another person helps you push on that door. It's still a door. Two people pushing on the door and I can't get through. But if I have enough people, say 10 people pushing on the door, boom, the door busts open. And all of a sudden I don't have a door anymore. I've got an opening. So that's the way it is with semiconductors. They're either not passing any electricity or they are passing electricity. And so you can get them to turn on and off. And the on and off relates in computer languages to ones and zeros, binary language, which is what we use for computers. So yeah, semiconductors. Okay. They're the ones, with the exception of aluminum, that are touching the that stair step line. And I think that's probably all I want to talk about in this video. Yeah, that's it. All right, thanks.